So real quickly, I want to talk about what we finished on Tuesday, which is this idea of concavity and inflection points, and we're going to talk a little bit about this. I'm only going to do we're not going to get up to the second derivative test, or we're going to get to the second derivative test, but we're not going to talk about that today. That'll be on Thursday. So the first thing that we want to make sure is that we have our terms correct. This is going to be concave up, and this is going to be concave down. And now we need to connect that to the idea of the derivative. And so you notice, and we're going to talk about going left to right here, and we're going to concentrate on concave up first. As we're going left to right, notice that the slopes of the tangent line increase. Okay, so like it's you kind of want to think of that as the slope of the slopes is increasing, and so that's going to produce a concave up shape. If coming from the left and the right, our slope of our slopes, the slope of our tangent lines start decreasing, that's going to show us that it's concave down. And an inflection point is where they change from, where the concave down changes to the concave up. Now that's going to be an inflection point, and this is going to have a lot of good meanings for us in application type problems. And so on the following page, they give you a test for concavity at the top there. And they say if the second derivative is positive on your interval, then the function is concave up. So what that's referring to is the fact that our tangent lines are increasing in steepness. The second derivative is positive. Okay, so the second derivative, the first derivative is increasing as we go through, and that would be the second derivative being positive, and that's producing our concave up. And vice versa, it's saying if the second if the second derivative is negative, okay, and so like think of that as, again, moving left to right, the steepness of our tangent lines are decreasing, and that's what the second derivative is measuring, this like the slope of our new slope. Okay, so as our tangent lines are decreasing, that implies that our second derivative would be negative, and therefore that's producing a concave down type shape. And then the last part, and then I'll go to that. Okay, and that's what's being said up here. Okay, and then the final statement in this, right? If C is a point on I at which the second derivative changes, okay, so then we're going from concave up to concave down, or concave down to concave up, then F has a inflection point at C. So then the rest of this is saying things that you should recognize from our discussions about critical points and maximum and minimums. Okay. So we may have, right, so we're going to be looking at our second derivative. We're going to be setting it equal to 0 to locate our potential inflection points. Okay, and then they're going through and saying, well, by the way, just because you found an inflection point or a potential inflection point doesn't actually mean that it's an inflection point. It's just a candidate. And so then we'll have to test the second derivative on either side of our potential inflection points to see what it produces. So, another thing that they're going to say is, well, usually it happens in a smooth change, but it doesn't have to be. It could also be where the derivatives don't exist. Okay, so again, this is all very, very similar to what we just talked about with critical points and local mins and local maxes. We're just dealing with the second derivative. So nothing really super big jump. It's just going to be a bunch of more terms and things to remember, okay? So they got some pictures down here. Okay, and so A is a classic, right, inflection point. Concave down, and now it's concave up. Okay, now they're giving you an example, right, where the second derivative was 0, but uh, the concavity doesn't change. Okay, so just examples of kind of what's going through there, and I would read that again, kind of with that in mind. There's a good example that at the bottom of this page, and I didn't take a picture of it, but I think you should look through it. It talks about, okay, what do you know when the first derivative is positive and then the second derivative is positive, okay? And so again, none of this is like super hard to keep, super difficult on its own, but to keep all of this straight is going to take a little bit of effort of really remembering what these rules. Okay, so I'm going to finish up by just doing number 57 from the homework. And at this point, you should be able to get up to 69 pretty easily. I do think you should spend some time trying to think through 53 and 55. Um, those are good thought processes and trying to help you learn these rules and theorems and all these little tests. But they say determine the intervals on which the following functions are concave up or concave down, and then identify any inflection points. Okay, so one of the things you're going to have to remember is which derivative does what. And the first derivative is talking about increasing and decreasing of the function, and the second derivative is talking about how fast the or even if the first derivative is increasing or decreasing. And so then that's referring to the concavity of the original function. Again, a lot of things to keep straight, but we're not worried about the first derivative at all, but we do have to find it first. So then 4x cubed minus 6x squared. Okay, we're going to just answer this question. We're not going to worry about anything that tells us right now. We're going to go straight to the second derivative because that's telling us all about the concavity. So now we're at 12x squared minus 12x. Okay, and so the first step is to locate any potential inflection points. And again, those potential inflection points come about when you set the second derivative equal to 0 and solve. Or another potential inflection point is where the second derivative does not exist. And we don't have that situation at all, so we're just going to locate these two. Again, get used to factoring here. So we're going to take out the 12x. So our two potential inflection points are at 0 and 1. And now we have to test on either side to determine, does the sign of the second derivative change on either side of these inflection points? If it does, then they are inflection points, and that's part of what we're being asked. And we're also going to keep an eye on its the value being positive or negative. Okay, so in the book they like to set up a little number line. I suggest you do that if that helps you think through what's going on. Okay, so we have a number line here. We got 0 and we got 1, right? That means that we have to test in 3 different spots. So, I'm going to pick -1, I'm going to pick 1/2, and I'm going to pick also like 2. And so we have to test those values in the second derivative. So then the second derivative here at -1. And, I don't know, maybe it's, I guess it doesn't really matter where we pick it, where we plug it in. So then that would be 12 plus 12 for 24. And then we're going to do it at 1/2 just to make sure. Let's see, that's 12 over 4 minus 6. So 6 would be 24 over 4. right? So then that's negative 12 over 4, so negative 3. I'm not sure why I did them with fractions, but it works out negative 3. And so we did go from uh, positive to negative at 0. So now we're saying, okay, one of our 0 here is an inflection point. And so now we can kind of talk about where it's concave up and concave down. So remember where the second derivative, why did that just happen? Sorry, the second derivative being positive refers to concave up. So anything to the left of 0 is going to be concave up. Okay, then it switches to negative, but now let's see if it changes at 1. So let's do the second derivative at 2. And right, we get 48 minus 24. So that will be a positive 24. So in fact, it does change. Both of our potential inflection points end up being actual inflection points. In between 0 and 1, it would be concave down. And then past 1, it's concave up. Okay, and I'm sure in the back they have it written out with set notation. Okay, so again, nothing like super hard, but it's just another layer of things that you got to remember. Okay, and that's what you got to do. You got to treat this as like kind of like a vocab quiz type situation. You got to really pound these rules into your head so that they become second nature to you. So you should be able to get up to 69 now. All you're doing is taking 2 derivatives and checking things out. On Thursday, we'll do the second derivative test and look at some of these application problems. And this stuff is big time, okay? So we got to make sure that we feel pretty good about these going forward. You'll definitely be asked about these.